Hello and welcome to this Zero Carbon Guildford third presentation related to low carbon energy and heat sources and their application to space heating. My name is Gordon Farquharson and I'm a volunteer with Zero Carbon Guildford and other local organisations and have been a Guildford MRA resident since 1985. Professionally, I'm a chartered environmental and building services engineer. This is Zero down at the bottom of North Street, and we welcome you. Our agenda in this talk covers the following ground. I want to set the scene first of all by just looking at some reference points from the Surrey Climate Commission and their perspective on space heating. I want to consider the government's direction of travel related to energy supply and residential space heating in particular. And I thought it would be interesting to have a look at our national grid and see how the sources of power, electrical power, are evolving and changing. When considering an alternative to your existing gas boiler, it's really important that you understand your energy demands. And I want to explore how you might determine this. Then I'll move into reviewing some of the main technical options and their limitations. Heat pumps, solar sources, photovoltaic and thermal, direct and off-peak electrical systems, and their linkage into thermal storage, electrical storage and hybrid systems. I'll make some comments about how to assess the best buy or the best solution for your application, and I'll have some conclusions at the end. In this presentation, I've used some typical numbers for illustration purposes. Your situation, your home, may have quite a different profile and requirement. So let's start by reminding ourselves of the Surrey Climate Commission report, and this was developed in March 2021 in its version 3, and it identifies a number of sources of carbon in Surrey. And it divides it into two parts: consumption-based emissions, which I won't be considering today, and direct emissions. And in the context of direct emissions, you can see from the graphic that housing and heating within housing is a significant contribution to carbon released into the atmosphere in Surrey. And that, along with travel and transport, represents the major elements of direct emissions that we have some influence over. The consumption-based emissions are also really important, and they are the subject of separate discussions. So we keep saying this, it's a sort of mantra through the two previous talks, and this is: don't forget the fabric first approach. Whether it's our existing legacy system or whether it's a new replacement energy source heating system, we really need to deal with heat losses in the best possible way we can. So we call this the fabric first approach. And the little diagram on the top left reminds us that energy loss, heat loss from our buildings, comes from air leakage, So that's natural ventilation, deliberate, or leakage in an uncontrolled fashion. Roof heat losses are a significant element, 25 to 35% of the losses from a building. Then we have walls, then windows, and then the floor. Now, if we consider these routes for heat loss from our homes, then the easiest one to address is that through the ceiling of our home and ultimately out through the roof. And this is clearly best addressed and most economically addressed by the addition and enhancement of the thermal insulation. Windows are reasonably straightforward to replace, but don't necessarily represent the win or the gain in the same way as roof heat loss. Leakage is a significant route for energy loss, and the diagram on the right just illustrates what is required today to do an air leakage test on a new built home, and the acceptance criteria for such a leakage test become more stringent as you move from the minimum standards within UK's rather poor building regulations to the much tighter standards that you would see in low energy solutions like Enerfit, Passive House and Leti. And I just show at the bottom because it was a product that I spotted recently that I was unaware of, and this is an enhanced air brick with a damper valve in it that allows specific control of naturally ventilated spaces, particularly floor spaces, based on the detection of moisture and air temperature within the enclosed space. So be aware, new products are arriving almost every day of the week. So let's move on and just see what the government believes we could or should be doing. So in October last year, October 2021, the government published its Heat and Buildings Strategy. And this was phrased as a plan to completely replace fossil-fueled heating like gas boilers with low carbon technologies such as heat pumps. And heat pumps certainly get most of the press. The end game is low carbon electricity based heating, with that electricity sourced from renewables and nuclear power. And the route to get to 2050 ultimately is that we need to replace around 23 million gas boilers. And this would mean we need to replace 600,000 annually to reach net zero 2050. And on the journey there, by 2025, new homes cannot be connected to gas, and 2035, no more gas boilers can be installed, new or replacement. And in parallel with all this, we have to increase our renewables and nuclear power generation. You can look at the energy mix in our grid power. And if you do this, you will see there is a long way to go. There are a couple of really interesting real-time sites that you might like to try and have a look at these. And there are a number of others, 2 or 3 others that I have looked at. And they illustrate the mix of fuel used to generate our electricity. And if you look at these, around 40% of our electricity is generally produced from fossil fuels. and that clearly needs to be reduced to net zero. But we need to remember that in addition to this, we currently burn 720 terawatts of gas annually, and a big chunk of this is used for space heating, and that's double the current 350 terawatt hours of electricity annually consumed. We'll just look at a page of real-time data, and just so you get a picture of what you can obtain from these websites. So on this particular day at 2:35 in the afternoon, we had a UK demand of 34 gigawatts of electricity. 38% came from fossil fuels, 26% renewable, 23% other sources, nuclear, biomass, and 13.6% from cable interconnectors from other countries. And I always find that interesting because I was unaware that we import so much electricity. What about hydrogen? You might ask. At one time, this was being postulated as a significant energy source. And it may well be in some sectors, but I'm a little sceptical as to whether hydrogen is going to be appropriate in a domestic application. I was looking at some recent research, and it was test work carried out at Keele University, and showed that it was possible to continue using existing appliances built to run on natural gas with some relatively modest modification, but only using a mix of 20% hydrogen and 80% natural gas, or methane. And this test only used 20% hydrogen because that's the maximum amount that could be mixed with natural gas without needing to change pipework and appliances. So a switch to 100% hydrogen via a gas grid would not be easy or cheap. And where would the hydrogen come from? The two sources are green, water electrolysis using renewable electricity, or so-called blue, which is steam reformation of methane, natural gas, with associated carbon capture. And this is a reference to the work carried out at Keele University, which you might find interesting to read for further information. So let's move on, and the next subject I want to address is understanding your energy consumption. This is absolutely critical for any consideration of moving from your existing gas-fired heating system, which most of us will have, to an alternative. So your home's energy use, things to evaluate, sources of information, energy bills, smart meter data, and I don't mean just from the little screen, I mean interrogating the raw data of your energy consumption, and being clear about timing of demand, what I call the load profile. And of course you could also evaluate the need from basic calculations of heat losses and energy consumption for domestic hot water, for example. So with gas, if we start off with an existing gas system, identify your main load items. So your gas boiler ultimately will need to migrate to an alternative, electrically powered, or maybe hybrid system with solar photovoltaic or solar thermal systems. You might have a gas cooker, oven and hob, which will need to migrate to direct electrical use. Now, this isn't all bad news, and some data I was looking at indicated that induction electrical hobs are 50% more energy efficient than gas or radiant hobs. Microwave use is also found to be very energy efficient. So obtaining information from your smart device data. So just repeating what I said earlier, the main sources would be smart meter data, and this is just an output from an Octopus Energy system, smart meter system showing gas consumption at half-hourly intervals. You can also obtain some important information on performance if you have a smart zonal control heating system. Now, what did I mean by home heating load profile? So from smart meter data, I can find some really good information, and this is very important when selecting a replacement or substitute heating system for your existing boiler. First of all, you need to identify and separate your domestic hot water energy. Now, this is likely to be easily identified by looking at your summer gas consumption. And on days when the heating is not required, then the gas use, assuming you can isolate cooking use, can be clearly identified, and it might represent 15 to 20% of your gas use. So that is information that you can obtain from a smart meter. Now, obviously, peak central heating load is in the winter. So identify your worst case winter days, kilowatt hours consumed, normal occupancy. So we might find over a particular day 7.5 cubic meters of gas is consumed, and this would represent, if you convert to kilowatt hours, 85 kilowatt hours, and if that was burnt over 15.5 hours during this winter day, and it turns off at night, the average consumption is 5.5 kilowatts as an energy rate. We then need to think about the energy profile over a 24-hour period. And evaluating the data in more specific detail, I can establish that the peak heat up power consumption, so this is heating up your house from cold, maybe at 6 o'clock in the morning, in this particular case was 15 kilowatts. And once the air temperature in the controlled spaces had risen to the target set point, a steady state temperature maintenance rate was 9 kilowatts. So I'm starting to understand a lot more about the energy required for the house from the data of the performance of the existing heating system. So with that baseline, I can start to consider some options for low and zero carbon heating technologies. To look at is heat pumps and consider how they work. And I'm using two diagrams to illustrate this. On the left is a refrigerator or freezer, and on the right is a heat pump configured for space heating. Now, the refrigerator, we're all familiar with this. It takes heat from inside the enclosure, and the enclosure is a small, very well insulated box, and rejects it to the outside. So we all know the inside of the fridge or freezer gets cold, and the radiator on the outside, which is the condenser, rejects heat into the room by convection. The heat pump works in exactly the same way, but of course it's in a reverse sense. So here it takes heat from outside, effectively cooling the outside air as its heat source, and it rejects that heat in the condenser inside our building into the heating system, whatever that may be. And in most cases, our domestic heating systems are waterborne, pipework distributing the heat in water to radiators or underfloor heating. So let's look a little bit more about the heat pump cycle and its efficiency. And its efficiency is described as coefficient of performance. And this is a very important term. So the refrigerant circulates in the direction shown in this diagram. So it's rotating clockwise. And the key components of the system are the compressor, the condenser, the expansion valve, and the evaporator. And the refrigerant passes through each of those components. If we start at the compressor sucks in refrigerant vapor and compresses it by doing mechanical work driven by an electric motor. That compressed vapor rises in temperature and it passes through the condenser where it is cooled and rejects the heat to our heating system. We then have a high pressure liquid that passes through to an expansion valve where the liquid is allowed to evaporate. The expansion valve is effectively an orifice, and as that liquid turns to vapor again, it sucks in energy and the cycle continues. And this energy is drawn in the case of a heat pump, from outside, cooling the outside air and transferring that energy into the refrigerant vapor. And that then goes back to the compressor. So the electrical power does thermodynamic work to extract heat from the source. And that source could be the air, could be a ground, or it could be a water source. The use of the term coefficient of performance is used, and this is the ratio of useful heat out to power in. So in the winter, I would expect a minimum coefficient of performance of 2 to 1. So I get 2 kilowatts out for 1 kilowatt in. And if the ambient conditions are higher, then that coefficient of performance rises. It should not be expressed as an efficiency. So sometimes I see this heat pump is 300 or 400% efficient. That's not a correct statement. Its coefficient of performance is somewhere between 2 and 4 to 1, depending on the operating conditions. The refrigerant should be a non-ozone depleting refrigerant, and typically refrigerant 32 is often used in domestic systems. And in large industrial systems, you might find ammonia and carbon dioxide being used as the refrigerant. So there are two principal heat pump options in our domestic applications. So the first is an air-sourced heat pump. So we have a device sitting externally to our home, and this extracts heat from the atmosphere, goes through the reverse cycle refrigeration, and imparts that heat into our heating system. Generally, air-sourced heat pumps are the cheaper of the heat pump installations to purchase and install. They have a lower coefficient of performance than ground-sourced, because in the winter the air source temperature will be much lower than the ground temperature, could be -10 versus +10 degrees. Noise levels can be an issue, so I'd be very cautious if I saw a heat pump quoted at 40 to 60 dBA at 1 meter. This could be quite intrusive noise level. You need a location for the external evaporator, the air source. And you may need some planning permission in certain cases, depending where the device is located. Now, the other main option in residences is ground source. So here we put coils in the ground in order to extract the heat from a part of the ground which maintains pretty nearly constant temperature. More expensive and harder to install than an air source, has a better coefficient of performance because the ground will be warmer on that coldest winter day. You need space and access to the ground source, and the ground source could be a horizontal or vertical array of piping. And the ground source could be shared across a number of properties or dedicated to a single property. So this diagram just illustrates a horizontal array, and some rules of thumb suggest the area could be close to or similar to the plan area of the property. An alternative for ground source is a board solution, and this could be applied to a single property, or a heat network could be provided such that a number of properties are engineered to share the same ground source. So let's have a little think about sizing the heat pump. So a heat pump always needs to be sized for the lowest source temperature, that winter design day condition. You need to select an output of your heat pump that meets the heating load requirement, considering both that peak load for warm-up and the steady state. Whilst you can get some information from your existing gas consumption, the load really needs to be estimated properly from a consideration of both heat losses from individual rooms within the building and a cross-check against existing consumption data. Now, if you required in your existing property, say a 25 kilowatt gas boiler, you would probably need a 12 to 15 kilowatt air-sourced heat pump and an 8 to 9 kilowatt ground-sourced heat pump based on the different coefficients of performance. But remember, best COP, we must have low condenser water temperature, that is in our heating system, and the maximum flow temperature should be around 45 degrees centigrade. Now, this will require a large surface area of heating surface in your property. Ideally, a heat pump system will use underfloor coils, but you may also use large area radiators and fan-assisted convectors. I show this table from my previous talk, and it illustrates the impact of different flow and return temperatures. So I just want to focus on the condensing boiler line. So classically, a condensing boiler will have a flow of 65 degrees and a return temperature of around 45 degrees to ensure condensing conditions. And a heat pump will have, in the heating system, a flow temperature of 45 degrees and a return temperature of 25. It is possible to select high temperature heat pumps, but they tend to have much lower coefficient of performance. Now again, from my last talk, remember I said that water radiators don't only radiate. Actually, 80% of the heat released into a space from a radiator comes from convection, with 20% emitted through radiation. When evaluating the output from a radiator, we need to consider the mean water temperature between flow and return, and as that mean water temperature drops, radiator output drops. So if I was to look at a change from a condensing boiler to a heat pump system, the delta T between the mean water temperature in the room falls from 35 to 15 degrees C, and the output of a radiator could drop by 50 or 60%. So you can see why generally you need a much larger heating surface. You may be lucky in your property that the radiators are oversized, but this needs very careful evaluation. We also need to consider the hot water cylinder, the domestic hot water temperature. Now, optimally, this should be greater than 60 degrees C to inhibit Legionella growth. Now, if I'm using a lower temperature heat source from, say, a heat pump system, then I would need to periodically heat this hot water cylinder to a much higher temperature to sanitize it using probably an electrical immersion heater fed from mains power or photovoltaic source. You need to make sure such a system that all the temperature detectors are at the right location and that they are calibrated and working correctly. Now moving on, let's look at some other energy sources. So when looking at solar energy, we have photovoltaic and thermal solar availability. Now in the UK, this certainly would be very unlikely unless it was an enormous array to provide sufficient energy for space heating. Therefore, we most commonly use photovoltaic diverted to a hot water cylinder or solar thermal for a hot water cylinder, topped up with electrical energy. We could also look at, and I saw recently from the firm I've illustrated here, a solar assisted heat pump. So this is a domestic hot water oriented system using a heat pump with an external solar panel through which the refrigerant flows, so it gets a high temperature external heat source. And this can operate as a high temperature heat pump for domestic hot water uses. Now I want to look at direct electrical heating, non-storage. And there are two options available for such an approach. So convection devices or infrared devices. So convectors, natural and fan powered, could be wall mounted or freestanding. And here, in the diagram on the left, the heat is released from the device and it heats the space, the air in the space. And the air in the space heats us, makes us feel comfortable, and also imparts heat energy to the cold surfaces in the room. Another option is a radiant panel solution, and here wall or ceiling mounted panels radiate energy, and that energy is absorbed by the surfaces that it heats, including us, and that induces human comfort. And the picture below, which I thought was just a bit of fun, illustrates sunbathing in the snow, in the sun, where the radiant energy makes the human body warm in spite of the low ambient air temperature. So direct electrical heating is a possible solution and would become affordable in a small space or highly efficiently insulated building, home, apartment. Off-peak. So there are new generations of fan-assisted night storage or off-peak heaters. And these have very low heat loss during periods of no demand. They're charged up with off-peak electricity, usually economy 7 type tariff. Can have adaptive control for charging and discharge. Cheaper to run than direct electrical heaters because they use off-peak energy. And they have a lower capital cost than heat pump wet systems. It's also possible to consider off-peak storage with a so-called heat battery. And these could be fed from photovoltaic energy or off-peak power. And there are a number of products emerging, and I've just taken an example from a firm called Tepio, and you might like to look at their information. And these are designed to replace gas boilers in smaller premises. They're charged off-peak, as I've just said, or from solar photovoltaic, and they're discharged at peak hours to provide central heating energy source and heat for domestic hot water. This theme is off-peak or photovoltaic charged phase change heat battery. So now, instead of just having a solid mass in which the heat is stored, this uses chemical compound that changes phase from solid to liquid and therefore contains both sensible and latent heat, improving the energy density of the storage system. So let's look at a few simplified cost comparisons based on a heat pump average COP of 2.5, and I've ignored the standing charge and hot water system consumption. So column 1, we have an annual heating energy consumption of 9,600 kilowatt hours. Before the removal of the current price cap, that might cost you 3.9 pence per kilowatt hour, which would be £375. At new gas prices, that could go up to £750. If I was using a heat pump with 2.5 COP at peak rate electricity, 32 pence a kilowatt hour, that would cost us about £1,230. Off-peak storage using an economy 7 could be £1,440. But I could have, if I had photovoltaic panels, a reduction by way of those photovoltaic panels. And if I was using direct electrical heating, convective or radiant, for the same heat output, I would be at around £3,000. So what about battery electrical storage to cover heating load? Seems a good idea, but actually if you look at the numbers, it would probably be challengingly expensive on batteries. If you assumed you wanted to store off-peak electricity and or photovoltaic solar energy to run a heat pump for a 75 kilowatt hour daily load, then you would need energy storage requirement of 38 to 40 kilowatt hours. This is the same size battery as a small electric vehicle, and the cost of a battery installation like this could be 15 to 20,000. I want to just look now at mechanical ventilation versus natural ventilation, and this is part of the fabric first approach. So why consider mechanical ventilation and heat recovery? And this is an indication of the configuration of such a heat recovery unit, and you can see in the centre of it is a cross-flow plate heat exchanger that exchanges heat from warm, moist exhaust air and imparts it to the incoming fresh air. And it is a heat recovery that can recover somewhere between 80 and 90% of the energy in the exhaust air. So natural ventilation wastes heat due to uncontrolled air exchange. So uncontrolled air exchange in terms of quantity and associated heat. In the UK, we mostly use low energy winter heat recovery. Elsewhere in the world, they might use summer coolth recovery. Now, we use such systems in conjunction with fabric insulation improvements to control or reduce uncontrolled air leakage. Importantly, there is no air mixing between the exhaust and the intake air. So in a property, we end up with something like this. So there will be an air handling unit, probably in the loft, which draws in fresh air, and it exchanges the heat with the exhausted air from the parts of the property where hot air, moist air, or odours are likely to exist. And we supply the reheated, the heat recovered air back to main occupied parts of the property. There is clearly a need to have ventilation ductwork in the property, and this may be a physical constraint in existing buildings. Let's look at some numbers for mechanical ventilation with heat recovery. Assume we've got a house, 550 cubic meters of internal volume with 2 air changes per hour ventilation. Assume the inside temperature is 20 degrees and outside is -5, so we have a delta T of 25 degrees C. Then doing some ventilation heat transfer calculations, if this 2 air changes was uncontrolled natural ventilation, we would be losing 9 kilowatts. And if we were achieving the same air exchange with mechanical ventilation and heat recovery, we would recover 7.3 kilowatts of that 9 kilowatts. So mechanical ventilation and heat recovery is always a solution that should be considered, and it is certainly a fundamental part of any low energy home design configuration. Some conclusions. There are many solutions and products out there, and it seems quite bewildering at times that there are so many, and new products and new propositions are being made every day of the week almost. Remember the fabric first approach, including consideration of mechanical ventilation with heat recovery. Quantify your heating requirements and load profile with time, and getting the information from existing heating systems performance data, smart meter data, and rigorous design. Select your system based on performance requirements, including considerations of space, noise, and maybe planning constraints. So finally, just some small print. I hope you found this useful. If you've got any questions, please don't hesitate to contact me